drugs, or ideas, what you consume influences who you become. On the Mind and Matter podcast, we learn together from the best scientists and thinkers alive today about how your mind-body reacts to what you feed it. Before starting Mind and Matter, I spent 10 years in academia doing scientific research. I got a PhD in neuroscience where I focused on neuroendocrinology and the neurobiology of behavior, and before that, I specialized in molecular, developmental, and evolutionary genetics. I use my scientific background to help parse and translate the information that guests share on the podcast. In addition to the podcast, I write long-form written content inspired by the show where I integrate what I've learned across episodes. I also have a free weekly newsletter where I provide you with upcoming guests, share links, and provide commentary on scientific studies and research that I'm reading, and more. Visit mindandmatter.substack.com to find all of my content. You are about to listen to the full episode, but there will be 1 to 2 short ads immediately following this before the conversation. If you would like to hear ad-free episodes and get early access before they release more widely, become a paid subscriber at the Mind and Matter Substack at mindandmatter.substack.com. Becoming a paid subscriber is a way to directly support my efforts, allowing me to make more episodes and higher quality episodes, and also helping to free up my time so that I can spend more of it on doing research and synthesizing results from the podcast and from the literature so that I can do more things like writing on the Substack, putting more content into the newsletter, and getting these things out more frequently. So if you want to support the show and get ad-free episodes, go to mindandmatter.substack.com. Hey everyone, I want to take just a minute to tell you about a really cool health monitoring device I've been using called Lumen. It's a handheld, pocket-sized device with a sleek design. The Lumen device measures CO2 levels in your breath, which allows their technology to determine the extent to which your body is burning fats versus carbohydrates. Lumen helps improve your metabolic flexibility, your body's efficiency in shifting between using fats and carbs for energy. I use this device in the morning or before bed or after meals or after workouts to track my metabolism. With just a couple weeks of use, I learned a lot about which foods were causing my body to burn mostly fat, mostly carbs, or both, as well as how long I needed to fast and how hard I needed to exercise to promote fat burning. Being able to track whether your body is burning fat versus carbs will help you figure out how your body responds to your lifestyle and whether or not your weight loss and fitness strategies are actually working. Lumen is great for anyone looking to optimize their health for either weight loss or athletic performance. Their easy-to-use app allows you to track your results together with what you're eating and how you're exercising, and it syncs with other devices like the Apple Watch. Click the link in the episode description to learn more and use the code MINDMATTER, MINDMATTER, to get 10% off your Lumen device today. That's on top of the site-wide sale they are currently running, and the Lumen device is eligible to be paid for with FSA and HSA health accounts. Check out the link in the episode description for more info. Masterjohn, thank you for joining me.
Thank you for having me. Great to be here.
Do you want to give everyone just a quick overview of, who you are, what is your scientific background, and what do you do today?
I have a PhD in nutritional sciences, which is essentially where biochemistry and molecular biology meet the food that we eat. So it's unlike dietetics, which is training in how to tell people what to eat from the perspective of conventional nutrition. Nutritional sciences is basically depending on exactly what you do in your work, it's either more biochemistry or more molecular and cellular biology, but it's focused on the basic science of what we eat. So whereas and actually there's a lot of intersection with pharmacology as well. So you could do studies of like, you eat some vitamin E, where does it go in your body? What does it do? Where did it get absorbed? So it's also a lot of the same type of research that would be done in pharmacology. It's just that instead of studying drugs, you're studying nutrients and the components of food. I went on to the academic route to become a professor of health and nutrition sciences. I did my PhD at University of Connecticut, Storrs. I did my postdoc at University of Illinois, Urbana-Champaign. While I was there, I taught first-year vet students vitamins and minerals, and then I became assistant professor of health and nutrition sciences at Brooklyn College in Brooklyn, New York for 2.5 years, tenure track. There I taught basic biochemistry to dietetic students who were becoming RDs. And I now have branched out on my own. So since 2016, I've been operating independently in nutrition science education on social media, in my newsletter, etc. And I now am co-founder of Mitome or Mitome, where we do mitochondrial testing to get down to the nitty-gritty of what is the best way we can optimize your own ability to produce cellular energy in your mitochondria with nutritional and related types of approaches.
Yeah, and so as you mentioned, you can study nutrients in ways that are akin to how a pharmacologist would study drugs. At the end of the day, we're talking about molecules that get into your body. They activate receptors. They do different things in our cells, and there's a lot that we could talk about with you in particular. For those listening, Chris is one of my favorite accounts to follow online. I believe there's only 2 Substacks that I actually pay for, and Chris's is actually one. And even though we'll talk a lot about nutrition today, you also talk a lot about the effects of prescription drugs on things like energy metabolism. And this is an area that's really interesting. It's really consequential, and it's often overlooked by people. We sort of naturally segregate things in our minds. We think of the foods we eat and we think of nutrition in that context. We think of the drugs we take, like the psychiatric medications, as affecting our brain. We don't necessarily always keep in mind that, all of these things can affect parts of our cells and parts of our bodies that we might not normally think about. So, things like SSRIs, things like psychiatric drugs can affect things like mitochondrial energy metabolism, and they often do in powerful ways, but many people don't really realize that. I want to start off actually by talking about what everyone is talking about right now, which is the whole Tylenol thing.
All right.
What was just announced, and what does Tylenol actually do in the body?
Well, what was, I'm not so sure that this was anything more than an acknowledgement of existing research, but what was announced was that the government is now interested in exploring the relation between acetaminophen, brand name Tylenol usually, and use during pregnancy and autism. And there are, some studies supporting a link and some studies that don't support a link. Hard to know causation from any of those type of studies, but they do open the question. Mm-hmm. And it's certainly biologically plausible. So the reason, essentially Tylenol is used as a painkiller, or, painkiller, you could, generally apply that to other anti-inflammatory uses and so on. And it's not classified exactly the same as the other over-the-counter painkillers and anti-inflammatories, but it's kind of doing almost exactly the same thing, where these are designed to reduce the production of compounds that are involved in the initiation of inflammation, such as prostaglandins, which are metabolites of the omega-6 fatty acid, arachidonic acid. Even that is, I think, profoundly misunderstood. So this whole generation of drugs comes from a time in which it was thought that if you block the initiation of inflammation, that's the best way to counter inflammation, because we knew what started it, but we didn't know what resolved inflammation. Mm. And now we have a decade or two of research showing that the same compounds that initiate inflammation are the central compounds that resolve inflammation.
So by blocking the initiation, you're also blocking the resolving of inflammation potentially.
Yeah. So, right. Exactly. So what that is it's a recipe for low grade chronic inflammation, which is
what everyone has.
Many people would argue is the entire basis of modern disease. I don't quite agree with that, but it's a valid hypothesis, and it's out there for a reason, which is most people have chronic low-grade inflammation. If you just take a marker, for example, you measure high-sensitivity C-reactive protein, or CRP, if someone is sick or they have an inflammatory disorder, you might see, 6, 10, 20, or way higher. But normal people should have, 1 or lower. But even if you look at that, what you see is, heart disease risk and risks of other chronic diseases are directly increasing, like within the, 0.3 to 0.7 range. So even though that's primarily used as a marker of an inflammatory disorder, what that shows you is basically chronic low-grade inflammation is extremely, at a very precise level, is extremely correlated to chronic modern disease risk. Mm-hmm. So that now, there's a number of animal studies where they use basically anything that blocks cyclooxygenase, or COX, which is the enzyme that converts the omega-6 fatty acid or arachidonic acid into prostaglandins, which initiate inflammation. Anything that blocks that, if you just take an inflammatory animal model, for example, you immunize the animal to its own collagen so it develops autoimmune arthritis. If you do nothing, you put the stimulus there and you remove it, what you see is, it's flat, the stimulus came in, the inflammation goes up, it hits a peak, and then it just kind of rolls over and it gradually declines over time. It goes back at baseline. And if you give them NSAIDs, non-steroidal anti-inflammatory drugs, or anything that blocks COX, what you see is you don't reach the same peak of inflammation, but then you also don't go back to baseline, and you just have this mid-level inflammation that just stays there forever. So these the whole not. This is a problem that is way broader than Tylenol,
right?
Because it's all the NSAIDs, which you could call like a cousin of Tylenol. Mm-hmm, mm-hmm. But really, the mechanism is it's anything that lowers COX activity, and so this, arguably, probably applies to a lot of herbs and haven't been studied. But
So basically, the use of these things, in essence, we're talking about trading a decrease in the peak amount of inflammation for chronic low-grade above baseline levels of inflammation.
Yeah, I mean, you would never make that trade if you knew you were making it.
Right.
No rational person would make that trade. It's just most people don't know that they're making it.
Right.
And if you just look at like the side effect profile, like it's very common to have GI problems and so on. And there's a lot of, there's a lot, every time you have a side effect profile like this, people come out and start saying it's an off-target effect, and they try to come up with some new drug or whatever, some way to hack around it. And they did that with they were like, oh, it's causing GI side effects because it's blocking COX-1, and COX-1 is very important in the stomach. So we want to block COX-2 because COX-2 is just associated with inflammatory disorders, and then like Vioxx gets pulled off the market, and they're like, oh, that's because it had an off-target effect. And it's like, no, blocking COX-2 is literally the worst thing that you can do, because it is not, well, for 2 reasons. One, COX-2 is both the initiator of acute inflammation and the resolver of acute inflammation. Yep. So everything that I was just saying is about COX-2, not COX-1. But then on top of it, although COX-2 is induced in acute inflammation in most of the body, it's constitutively expressed, meaning it's always just baseline is high in the gut, where it is fundamentally responsible for preventing autoimmune reactions. And there's another thing that most people don't know. So generally, people who work with autoimmune gut disorders think that the normal baseline is to fully digest all of your food, and the immune system never sees it. And so you get, and this is pervasive in anyone who's talking about, celiac disease or non-celiac gluten sensitivity or any of this stuff. People think that the problem is that the immune system sees the undigested food protein, but that's not what the GI research has been showing over the last 20, 30 years. It's that the normal thing to do is to take partially digested fragments of food and purposefully import them into the gut-associated lymphoid tissue, or the GALT, where the immune system will recognize it and learn that it is a food, and will therefore teach itself to not form an inflammatory reaction to it. And what's the primary mediator of that? COX-2. So that's one big problem, is that the on target mechanism of not just Tylenol, but the whole entire class of over-the-counter anti-inflammatory medicines is fundamentally bad for you. It's when the drug is doing what it's supposed to do, it is awful and is a major driver of chronic disease. So that's one point. Now, the second point with Tylenol is that a small proportion, but a predictable proportion at any dose, is converted into a chemical that's abbreviated NAPQI. And this is detoxified through several means, but one of them is glutathione.
And what is glutathione?
And glutathione is a tripeptide, meaning it has 3 amino acids. It's made from the protein that you eat in your diet. And it is the chief antioxidant of the cell. It's the chief detoxifier of the cell and the body. It is a key regulator of many functions, including mucus fluidity. So it's very important in the lungs, where it's not only protecting against oxidative stress, so its antioxidant role, but it is also protecting. So for example, if you get sick and you cannot cough up the mucus, that's because you don't have enough glutathione to break the disulfide bonds between the mucus proteins, so they all get stuck together, and the mucus is too big for you to be able to cough up. And a lot of decongestants are actually substitutes for glutathione, where they also are capable of reducing disulfide bonds, and so they help break apart the mucus. Glutathione is also the endogenous bronchodilator through formation of a compound called nitrosoglutathione, which forms when nitric oxide, which is also made from protein, specifically the amino acid arginine, combines with the glutathione. That is the endogenous bronchodilator. And if you look at asthma, it's just directly correlated with the worse asthma you have, the lower your lung levels of glutathione. And if someone winds up in the emergency room with an asthma attack bad enough to send them there, then their nitrosoglutathione levels can be 0 in the lungs. So inhalable steroids are also just substitutes for glutathione.
Right.
And
so you don't want to.
Acetaminophen use is also heavily associated with asthma in some studies.
Yeah. So glutathione, powerful natural antioxidant made from protein. You don't want your glutathione to be depleted.
No, you don't. And I do think that I think doctors tend to misunderstand this point, because they think so medicine uses a reality distortion.
Oh, shit. You froze. I don't know if you can hear me right now.
Them into binary yes or no's so that it helps them make treatment decisions. And so was the internet cutting out?
Yeah, it was, but I can hear you now. So they use a reality distortion field.
Right. Yeah. Okay. So so by using these reality distortion filters, they can sometimes get caught up in conflating them with reality. So in the case of acetaminophen or Tylenol, doctors are thinking about it, and toxicologists, et cetera, are thinking about it from like, is this person going to have a clinically significant level of glutathione depletion in their liver that is going to require treatment? And so, they get caught up in this dose response saying, well, you have to use so much Tylenol in order for that to happen. But biochemically, you start glutathione depletion with a normal non-toxic dose.
Right. And that's sort of invisible to someone with a clinical mindset like that, because, that lower dose isn't going to result in the patient having to come in and get some kind of treatment. But that doesn't mean nothing bad is happening.
Right. But that doesn't mean that it's not going to contribute to asthma. It doesn't mean that it's not going to contribute to autism. You're going to have no clue if you're not looking for it. So, right. and then these endless defenders of pharma at any cost come out of the woodwork and say like, well, not every, so many people use acetaminophen during pregnancy and almost none of them have autism. And that's really a BS argument, because when you're, there are many other things that deplete glutathione.
Yeah.
So let's just, suppose that glutathione depletion is at a certain developmental stage is an important driver of autism, which, there's plenty of literature to support that. Not that it's the only thing, but it is one of the relevant things. It's like like, another thing that depletes glutathione is not eating protein or fasting, so you can have oxidants, et cetera, et cetera. So like there are many things that are going to impact to a very large degree the baseline level of glutathione in the liver, or in any other tissue. And so not everyone's going to react the same way to a certain dose of acetaminophen.
Right. So bottom line, even though most people are taking, what would not be considered a high dose of Tylenol, even the normal doses of Tylenol are always going to result in some amount of the production of the NAPQI molecule that can do nasty things.
Yeah. Yeah. It is generally, it's generally just proportional to the dose. It's not a spillover effect. So it's not like you have to consume like a very high dose before it starts happening. It's just, a small percentage is always converted to that. And there are things that will, that will vary in the background that make the dose different between different people. Because there are, cytochrome P450 enzymes, which are the detox enzymes that can be influenced not only by genetics, but also by your diet and your exercise and your fasting cycle and alcohol and all kinds of things like that. So it's genetics plus recent environment plus average environment over the past several weeks that is all going to spill into, in a given person on a given day, how much of the acetaminophen gets turned into NAPQI. But but like if you just take the average population, it's just sort of like a predictable drip stream out of the dip. So it's more like it's not like a toxic dose allowed you to make some of that. It's just that you took more of it, and so you wound up with more of it.
Yeah. And so one more point I want to make here that you mentioned is no new information has actually come out. This announcement was basically just bringing attention to this whole area. These are all everything that you just mentioned. These are all things that we've known for quite some time. Many people have argued, or at least some people have argued, that Tylenol might have a link to autism via glutathione depletion and oxidative stress. There's no direct evidence proving that for an absolute fact, and people argue about it. But there's really no new information here. We're talking about stuff that's already been known.
Yeah. It is, but it does make a big difference that the government is going to, start looking at it. But, again, I don't know what Kennedy has on his desk, but I can tell you for sure there's all sorts of hidden data because, firing all the people who are running the CDC now allows us to go and look at the CDC data that they've been hiding, because the CDC keeps its own data, and it's sort of like a good old boy network is, I don't know if it's even the right word. It's more like an exclusive club that's invite only. So you cannot. Most other public data, like NHANES, for example, the National Health and Examination Nutrition Survey, they do this every, in cohorts. They measure all kinds of stuff about nutritional intake in Americans, and then they make the data set public. And if you're a researcher, you can go download the NHANES data, and you are, they made the data, but you are analyzing it. And so it's just like an open source where there are many people that will publish papers on the NHANES data, not because they generated any of it, but because they did a new novel analysis. And so their contribution was they came up with a hypothesis about correlations that could be found in the data. The CDC has all kinds of data where the only way you can analyze it is to get someone in CDC to invite you to analyze it. And so to say that there's nothing new, like there absolutely is tons of CDC data that could be reanalyzed, and we have no idea if we know it until we know it.
Yeah.
So I would not rule out that they have data behind the scenes,
right. That they've seen that nobody else has.
Seen. Right. Yeah.
Interesting. I want to spend quite a bit of time talking about SSRIs. Obviously, these are widely prescribed and widely used. You've written a fascinating series on these. Let's perhaps start with just some of the basics of serotonin itself. I think when most people hear the term serotonin, whether it's a layperson or someone educated on the stuff, they think the brain, they think about mood, they think about, those types of things. But it's far from the full picture when it comes to serotonin. How would you describe what serotonin does, generally speaking, and how much of it is brain-centric stuff and how much of it is other things that people don't normally talk about?
Well, I think you get, it's very instructive to just look at the name of the molecule. So serotonin means sera, that it is found in the serum, and tonin refers to it being able to regulate the tone of the vasculature. So it's named after its presence in the blood where it constricts blood vessels. That's what it's named after. And it was named this around slightly after, but around the same time that it was named by other people enteramine for its presence in the gut. And then, a few years later, they realized that they demonstrated it's the same molecule, and the name serotonin stuck. But it's very interesting that neither of those names have anything to do with the brain. So that right there tells you something, which is that serotonin is a whole body molecule, and that's primarily found outside the brain. Now, if you look at SSRIs, you can see how they hijacked and perverted serotonin science and converted it into their marketing materials. But what you see is the fundamentally deceptive name given to the drug. So the R in SSRI is reuptake, and the word reuptake doesn't mean anything outside of the neuronal synapse, where the idea is you have a neuron number one that is meeting with neuron number two. Neuron number one puts out serotonin. It acts in the synapse in a neurotransmitter fashion, and then it takes it back up. It reuptakes it in order to remove the signal from the later neuron. You don't talk about reuptake into a blood vessel or reuptake into a muscle or reuptake anywhere else. It doesn't mean anything anywhere else. And so it implies that SSRIs are acting exclusively in the brain, where they act exclusively at the neuronal synapse, which is total nonsense. And it's like, how on earth do you have the word reuptake talking exclusively about the synapse, along with the word serotonin, naming serotonin after its occurrence in the blood? Like there's something wrong here. So if we put our heads on straight about it, there is serotonin in the brain. It does act at the synapse, but 95% or so of serotonin is found in the gut, first of all. And that is absolutely not because the gut is your second brain, which is a kind of, like are there things in the gut that can get into the brain through retrograde axonal transport through the vagus nerve? Sure. Are there things in the gut that spill out into the blood and then
it's doing lots of things other than neurotransmitter like behavior in the gut and elsewhere?
Well, most fundamentally in the gut, it's regulating gut motility. It's in the gut because it regulates the function of the gut.
And that would also immediately.
The gut is also a reservoir for whole body serotonin synthesis. So in the blood, it's mostly stored in platelets, and a lot of that serotonin makes its way to the lungs. That is, a lot of serotonin that is made in the gut does wind up in the lungs. Not a lot of serotonin made in the gut winds up in the brain, though.
Yeah, and this would also immediately explain why, for example, SSRIs have the side effects that they do, common ones being gut issues.
Oh yeah, nausea and vomiting are I wouldn't say they're universal, but they're not only are they extremely common in the first couple of weeks, but they're such a problem that a lot of resources have been devoted within pharma to try to hack some way of kind of like the two holy grails of SSRI research over the decades that have never been obtained are, can we make these things work right away instead of taking 2 weeks to kick in? And can we make them not cause a couple weeks of nausea and vomiting before we get to the therapeutic effect? Because if you start with the adverse effect for 2 weeks before it goes into the benefit, it's not a good look.
Yeah.
So, but they've never been able to do that because pharma, and this goes back to the inflammation thing. They've never been able to come up with a drug that reduces inflammation in a way that doesn't totally completely harm you. And sometimes the trade-off is well worth it, right? Like if you've got severe Crohn's disease or severe ulcerative colitis or something like that, you may need one of these heavy duty inflammation blockers, but it's not that it doesn't have a pretty significant trade-off. It's that the trade-off just happens to be worth it in that case. But I mean, providing that you have not found a way to resolve the issues without the drug. But it's just pharma does not have. So this is the problem. The problem is that pharma's tools are primarily biochemical, and they are not primarily physiological. So you just have layers of everything where inside the cell you have, one enzyme acts on one substrate, converts into something else. This is like a biochemical pathway. Then you have the organization of the cell itself, and you have these regulators and stuff, and you get into molecular biology. You have the cell, you have cellular biology. But when you start, putting together a tissue and then have another tissue somewhere else, and you've got all this crosstalk and communication, you get like each one of these things is like an instrument inside a symphony, and the physiology is what produces the phenotype. Like it's the symphony orchestra of all these parts working together that produce something like mental health or depression, or that produce something like inflammation or healthy tissue function. And so the problem winds up being that a lot of the stuff that you want to happen is actually at the physiological level. And nutrients are interesting because nutrients are as a molecule working at a biochemical level, but you're putting raw materials. When you eat nutrients, you're putting raw materials into your body, which has a physiology that knows how to selectively take that nutrient up from the food, discard what it doesn't want, distribute it into many different places in different proportions, and put it into one part of a cell and not another, because we have, our entire evolution has wired us to be able to do that complex work with that. All pharma drugs are xenobiotics. Therefore, they are all unfamiliar to the body. Therefore, the body is primarily trying to get rid of them, not to do anything with them. And what you have to do is you have to supply it at a dose that does what you want before the body gets rid of it. And you don't have a way to make it go into specific places and not others. And, there are some limited ways you can do that with pharma, with route of administration, for example. Like if you inject something instead of taking it orally, that's one tool you can use. You can enterically coat something so that it, passes the stomach and goes into the small intestine. But you don't have complex control over it. And usually whatever pharma is trying to do is not what actually happens. So if you look at mRNA vaccines, for example, they thought, like, the story was, these get reliably uptaken by receptor-mediated endocytosis, which means they bind to a receptor, get recognized by the cell, pull it in at the site of injection, don't get integrated into DNA, lasts for a little while and then go away and never leaves the shoulder. And But even before they ever brought out the COVID vaccines, there was quite a body of literature on how lipid nanoparticles get metabolized just like lipoproteins. So, that like if you just took what was like they took one part of the story that was convenient to the story they were trying to tell, and they left the rest out. And so it turns out you inject someone with mRNA to make a toxic protein that in and of itself is capable of killing a mouse with pneumonia. Turns out that it goes to the lungs and the mammary glands and the heart,
right.
kinds of other stuff, right? So pharma really does not have control over where things go, except to an extremely limited sense. But when I eat 30 nutrients in my food, my body does all kinds of things that I'm not smart enough to do with them by putting them to specific uses in specific tissues. So pharma is very much handicapped with this. And, as it turns out, if they wanted to prevent the first 2 weeks of no benefit to depression, what they had to do was they had to get an SSRI that would somehow prevent serotonin in the synapse from exerting negative feedback on the first neuron to stop its own serotonin production. Because it's basically like as soon as you put too much serotonin in the synapse, the first neuron reacts by being like, oh, I have enough serotonin, I'm not going to put it out there. Right. And so you get this re-equilibration, and finally you get this higher equilibrium level that settles out. How are you going to make something that allows serotonin to activate the second neuron and not have a negative feedback loop on the first? They spent 20 years and they got nowhere. And then with the nausea, it's just the same thing. Like, oh, can we inhibit HT3 and HT4 receptors in the gut? Well, yeah, you can. But as it turns out, HT3 and HT4 receptors are also in the brain, and they're also on the mitochondria, which is a whole other central part of the story that no one knows about.
Yeah. Well, let's connect the dots here in terms of how SSRIs affect mitochondria. Let's maybe start with where serotonin actually comes from. So how do you go from tryptophan to serotonin? How does that connect into melatonin? And let's maybe go that route to start talking about how SSRIs actually affect energy metabolism in the mitochondria.
So tryptophan is an amino acid that you get from food. Most food proteins, all food proteins will provide some tryptophan. It's generally pretty well spread out. There's some variation in the foods. Really, collagen is the only whole food protein that is very low in tryptophan. That tryptophan then gets converted in several steps to serotonin, which can then get converted in 2 more steps to melatonin. And that is, the bulk of that is happening in the gut, but it happens to some degree in every tissue and probably every cell, or at least most cells. And it also happens in the brain. Most of that is happening in the cytosol, not the mitochondria. The cytosol is a general area of the cell. If you think of the cell as like a house with many rooms, and the mitochondria is one of the rooms, the cytosol would be the hallway. It's the part that connects everything in the cell. So the conversion to serotonin is generally happening there, whereas the conversion to melatonin is happening in the mitochondria. Until fairly recently, most people were mostly familiar with melatonin being synthesized in the pineal gland, which secretes it at night in order to regulate the sleep-wake cycle. But as it turns out, first of all, at night, that melatonin rapidly disappears from plasma. It does not rapidly disappear from plasma because it was broken down. It rapidly disappears from plasma because the cells of the whole body take it up very quickly. And it's distributed throughout the cell, but a big chunk of it goes to the mitochondria. And so under normal healthy conditions with a normal sleep-wake cycle, probably most melatonin in most cells in their mitochondria is actually taken up at night from the circulation by that was made in the pineal gland. But if you have a stress situation, then the cell, and they don't have enough melatonin, the cells will do everything that they can to make melatonin in their own mitochondria. But that can happen both by taking up serotonin from the circulation or in the brain from the intracellular space, and then it can also any of those cells can just ramp up their own synthesis of serotonin, tryptophan as well.
So normal everyday conditions, it gets dark out. Your pineal gland is making melatonin that gets released into circulation. That is where much of the melatonin comes from. It is taken out of circulation and cells uptake it. But under stressful conditions, other cells outside the pineal gland, elsewhere in the body, can make their own serotonin or can make their own melatonin.
Yeah, that's right.
And so what is the melatonin actually doing? Why is it being made, and what does it do?
Yeah, there's a bit of a mystery here. So in the mitochondria, melatonin is definitely an important antioxidant, but there is a body of research suggesting that both serotonin and melatonin are especially important to mitochondrial function in the context of hypoxia. And that, a lot of people, when they hear this, they think like it's relevant if they live at altitude, or they think that it's relevant if they're getting suffocated. But in fact, hypoxia is always relevant. And that's because there are always some cells in some of our body, in parts of our body, that are getting less oxygen than they would want at any given moment. And so when you take a breath, your breath goes into your lungs, but parts of your lungs, there are many parts of your lungs that have the capability of gas transfer, and you are always flooding your lungs with poorly oxygenated blood in order to take that oxygen, right? And so if your breath puts more oxygen to some parts of your lungs than others, and you can reduce the differential if you practice very good breathing practices, but the average person is breathing way too shallowly and is, barely using their lungs at all. And James Nestor has a good book on this called Breathe. And one of the things he talks about is in emphysema patients, you can teach them to breathe you can teach them to just exhale for like 4 more seconds per breath, and they wind up getting a much better clinical condition. And it's not because you're getting rid of the emphysema. It's because the only emphysema part of their lungs is the part that they usually use. And most people are like not using 2/3 of their lungs. And so, so for the average modern person who's not taught to breathe very well, this is extremely relevant in every breath. But even if you breathe very well, you're not going to have equal oxygen distribution to every part of your lungs.
There's always going to be a patch of the lungs that gets less oxygen than another patch. Right. And I'm sitting on my butt right now. Maybe I'm pinching a blood vessel, and there's always going to be tissues that are relatively oxygen deprived to some extent.
Right. So even at the point of breathing, serotonin is acting as the traffic cop of the lungs. It's shutting off blood flow to poorly oxygenated areas of the lungs, which preserves the circulatory function in the lungs for the better oxygenated parts, and it helps with efficient oxygen delivery. Then there are other things like, you wake up in the morning, you get light, your metabolism ramps up, and you have to recalibrate by going from the sleeping state to the wake state to get your oxygen consumption up. In that interval, you're in a state of relative hypoxia because your energy demand has gotten up faster than your energy production. And by the way, light is also the primary determinant of serotonin levels in the brain. So you're also getting a serotonin spike at that exact same time. You start exercising, those cells are going to be immediately hypoxic. It's going to take you up to 20 minutes to fully get the oxygen flow going. And even if the oxygen gets fully going, in an endurance race, for example, you need to endure, but you also need to go faster than the other people if you want to win the race. And so you're going to, even if you're maximally aerobic, your ability to cut into the relative hypoxic state by adding energy metabolism on top of what oxygen is doing is going to determine whether you can get your speed higher than the next person to win. So, hypoxia is constantly relevant in all sorts of ways. And before you go down the rabbit hole of what do serotonin and melatonin do in that state, what you would think happens, and what every textbook says happens, and what every review says happens, is that you shut down mitochondrial respiration in favor of anaerobic glycolysis. So if the mitochondria is the cell's power plant, creatine is the cell's energy grid, glycolysis is like a local power generator where you're saying like, okay,
if the grid goes out, I can turn on the generator and light my home for a while.
Yep. Yeah. Now, as it turns out, the more you get serotonin flowing into the mitochondria to generate melatonin, the more you don't need the local power generator. The respiration keeps going without oxygen. Why?
Yeah,
I don't know. I have a couple ideas. I think either it's a redox thing or it's a photon thing or it's both.
Yeah, but in effect, something would be substituting for oxygen, basically.
In effect, the presence of melatonin in the mitochondria is allowing more respiration to occur than you would expect with any given deficit of oxygen.
Interesting.
Yeah. So if you imagine that, like we were saying before, there's always some degree of relative hypoxia, relative demand going on in the body. That means, your ability to maximize, your ability to make your ATP meet the total demand for it is fundamentally driven by the presence of melatonin in the mitochondria, which puts on a whole different color on what SSRIs are doing, because they're not specific to reuptake. They inhibit the serotonin transporter, which means they inhibit it everywhere, which means SSRIs are fundamentally blocking the ability of melatonin to act, to be in the mitochondria, and are fundamentally impairing the ability to respond to oxygen deficits and maximize ATP production.
So, I mean, that would be a problem.
Well, it's a problem if you want to thrive.
Yeah. So okay. You've come up with, I think, is an interesting way of thinking about like sort of the fundamental role of serotonin, both in tissues outside the brain, but also in terms of what it's doing in the brain, and even, how it acts as a potential antidepressant. We can talk about that. You describe serotonin in the Substack series that you wrote as a stress coping chemical that exerts its action primarily through dissociation. So break down what that means for us, both in a brain context and a sort of depression mood context, but also somewhere else in the body.
Yeah, I think that I think that if you just think about it from the neurotransmitter perspective, the way that I think about that is you want a happy medium in terms of the degree to which you associate with your stress. And I think one of the important insights of any tradition that has allowed people to act as an observer of their own thoughts. So, for example, Buddhist meditation, Christian desert fathers, you get this insight that comes out of that our thoughts are not ourselves, and our emotions are not, we are not those things. And I think, your baseline, if you've never thought about it before, is you think whatever goes, through your head is you. And I think that you don't want to be so separated from your thoughts and emotions and feelings that you don't learn from them and don't use them in productive ways and don't take insights about yourself from them.
But you want there to be some distance so that you're not constantly caught up and identifying with those things.
Yeah. I mean, if you the average person has 4,000 thoughts a day, and if you were giving equal attention to all of them because you were unable
to dissociate from any one of them,
yeah, you would be psychotic.
Yeah.
And, and that is some people's
Right.
problem. The schizophrenics with flight of ideas have that problem. And so you want your mind to be like a fluid net where thought goes through and you can choose to catch it or not according to whether it be productive for you spiritually, mentally, emotionally, work, whatever. But if there's some value in catching on to that thought, you want to hold it there as long as it has value. And if there's not, you want to let it fly. And so I think that serotonin is one of its roles is to regulate the amount of distance that we have from our thoughts. And you want it to be in a happy medium because you want a little bit of distance, but not too much. And in
the context of mental health and depression, this would explain why SSRIs could be beneficial for some people with their depression, because it allows them to sort of separate from those depressing thoughts a little bit. It would also explain things why people say that they feel flat, that, sort of emotionally flat on SSRIs. There's almost, you might say that there's too much distance created there, but
well, I mean, if you, another aspect to this is that serotonin is responsible for the avoidance of punishment. And the way that's studied, what it really means is altering your behavior in a way that avoids adverse consequences. But the way they study it is to see, if I zap someone, do they stop doing the thing that makes them get zapped? And so it's kind of framed as response to punishment. But you'll see this come up in the OCD literature because SSRIs are the first line of defense for OCD. And in the OCD literature, the rationale for this is that inadequate serotonin generation production in the brainstem is causing the OCD brain to not learn from its mistakes. So it's like these intrusive thoughts and they ruin your life, but your brain doesn't fundamentally recalibrate to be like, oh, that really sucked. Let me do it differently this time. And so that's a manifestation of the brain being unable to adequately respond to punishment. But if your brain is too responsive to punishment, that makes you a coward.
Right.
If you can't have a difficult conversation with your spouse, it's too much serotonin is going to do that. And I do think that there is kind of a wave of cowardice. I'm not saying it all comes down to SSRIs, but it's certainly like a population level like issue of concern that you see these maybe we capture it more on video, but there was a time where, and I do think this is cultural. Like, I think, if in Greece, you're on a bus and a pregnant woman comes on, and you don't give up your seat for her, the bus driver is going to call you out and just confront you directly on the mic. But then you see these videos from Europe or whatever, and it's like someone just comes out and starts stabbing people, and people just like catch it on video and they do nothing, and it's just there is some kind of like deficiency of there's a
to confront the difficult situation.
A
potentially punishing situation.
And so this is not a situation where you want to infuse like mass increase in the avoidance of adverse consequences through boosting synaptic serotonin. And I think these are. So in my mind, I always want to find the cleanest way to tie everything together. And I'm sure someone could critique me by saying like, oh, you're trying too hard to fit these into the same bucket. But to me, the avoidance of conflict, cowardice, and stress coping, they're all kind of sides of the same coin because they're all ways of dissociating you from the adverse thing, right? Whether it's behavior or it's through conceptualization. And I and this is, it's very controversial, but if you subscribe to the idea that SSRIs are playing a role in school shootings, then it's like, the MAC or suicidality, certainly they play some, that is some level of side effect. You consider your reality to be an adverse consequence, and you dissociate yourself from it either by destroying it or destroying yourself.
Right.
And then, you look what it does in the rest of the body. It's like, what does it do in the gut? Well, it's like the more serotonin, the more you dissociate from your food, right?
So like if you have a stressor going through your gut, you want to get it through.
It either goes out that way or it goes out the other way.
So and it's all about this sort of happy medium, right? You want to speed up your gut motility to get the stressor through.
Yeah, otherwise you're constipated.
but if you keep going, right, then you start getting vomiting, diarrhea, that type of thing.
Right. Yeah, I mean, it's just like the Bristol Stool Quality Index. You want to be like a 4. And there's a mental version of that, and it's I don't know what you call it, but it's the happy medium.
Yeah. Interesting. So what are some of the long-term effects of SSRI use, and how does this tie into mitochondrial metabolism?
Vinay Prasad just co-authored a paper that looked at all the SSRI trials, and Prasad is the one he's the evidence-based medicine guy who got tapped into FDA. Then he left over a controversy over a drug approval, and then now he's back. But anyway, this review it compared the use of SSRIs in clinical practice to the use of SSRIs in clinical trials. And what you see is that almost every SSRI trial is 12 weeks or shorter. 88.5% of them are 12 weeks or shorter. That paper said that the longest one is 1 year. I'd have to go look at inclusion criteria and whatnot. I've seen some people say, oh, actually there's a 2-year one, whatever. But the point is that almost all these trials are super short. Whereas the average person put on an SSRI is put on the SSRI for 5 years, and that's the median. So you've got a lot of people that are on it for way longer than that. Now, if you look at the trial evidence, one thing that you see is that even within the trials, and not all the trials measure discontinuation syndrome or withdrawal syndrome, but a bunch of them do. But most of them are 12 weeks long. And so what the trial evidence shows is that there's some level of being on an SSRI that's 3 or 4 weeks long, maybe is the maximum, where maybe 6 weeks, but somewhere around the 4 to 6 week mark, you're starting to get dependent on the SSRI, and you can get a withdrawal syndrome from it. And there are various symptoms associated with it, but they are not all relapse of depression. So if you look at a review on this, they'll categorize them between new onset symptoms and relapse of depression. But if you look at the observational literature, you get, a much darker picture of what's happening than what the trials suggest, both because what the trials suggest is that it's not that common to have a withdrawal syndrome. When you do, it's pretty moderate, and it's usually over within 1 or 2 weeks. But if you look at the observational literature, where you see people on the SSRIs for much longer, what you see is that as you go from 6 months to 1 year to 2 years, you have a dramatic increase in the incidence of withdrawal syndrome, in how long it lasts, and in how severe it lasts.
Yeah, that's exactly what you would expect, right? Like if you're going to do the trial, if you're on it for longer, you're probably going to be more likely to experience some kind of withdrawal or a stronger withdrawal.
You would think so, although I don't think that's totally universal. Like it's for example, like I don't think years of drinking coffee has changed what happens when I go like a week without coffee. I think it has made it. I do think that like the longer someone drinks coffee for, the more likely the incidence of dependence certainly goes through the roof the longer you've drunk coffee for. And maybe to some degree the severity, but it kind of plateaus out. You take someone who's been drank 2 cups of coffee a day for 5 years, and take someone who's drank two cups of coffee a day for 10 years. I don't think you're seeing like a dramatic difference in what happens if they go 3 days without coffee, or 2 weeks, or 6 months. I think you're seeing a plateau point. And maybe that is true with a lot of other drugs, but I'm just saying it's not a general feature. I don't think it's just across the board true of dependence.
But basically you're saying that when you look at the trial data from the clinical studies, most of which are 12 weeks or less, you maybe see a little bit of withdrawal, but it's not so bad. It's not so much. But when you look at the observational literature where people are on SSRIs for 1, 2, 3+ years, you seem to see much more withdrawal and more severe.
2 years, you're looking at 96% incidence of withdrawal symptoms. You're looking at 38% of people who try to get off it just go back on it because they can't tolerate life without it.
So almost everyone has withdrawal symptoms when they're on it that long, and some of it is so severe that they have to go back on because it's so terrible.
It's close to 100% at 2 years, and I wouldn't say some. At 38% is over a third. So it's almost 3 out of 3 people get withdrawal syndrome. And in 1 out of 3, it's so severe that they give up even trying to get off it. But if you look at, there's a smaller literature on protracted severe SSRI discontinuation syndrome. And the median person has been on SSRIs for 8 years in a study like that. So what you're looking at is when you go from 6 months to somewhere around like 4 to 6 weeks is when you start to get some level of dependence where you're going to notice going off it. 6 months to 2 years is the big range where that's increasing, where like you're getting an increase that basically just everyone has something, and a third of people have it really bad, and it lasts longer. And then when you get up to like 5-8 years, that's when you feel like the mafia put you on it, because it's like, now I'm getting side effects that I can't live with, and that drives me to go off it. But like 8 years later, I still have catastrophic problems. So I had one client who had new onset chronic fatigue after so he was in his early 20s. He went off the drug because he's getting sexual dysfunction from it. This is sertraline. And but going off the drug caused new onset mitochondrial dysfunction that was so severe that there was a whole year that he couldn't stand up in the shower by himself. And there was a month where he couldn't get out of bed, and he had a portable bedside toilet, and he had someone giving him a sponge bath.
His energy was so low? Like he just couldn't exert himself? Well,
yeah, I mean, I wasn't there to observe it, so I can't tell you how much was muscular and how much was neurological, but it was probably a mix of both. Mm-hmm. And then there's you get like these the brain zaps, right? So there's, and you look at it's an internet phenomenon that people call all these things brain zaps, but when you look at the surveys of what people mean by them, the majority of people are talking about feeling like electric shocks are going through their head.
Yeah.
And but you get people that are saying it's like the video of their life experience is buffering, or these various other things where it's just like you went blind for a second, or just like the whole room shook for a second, or it's just literally like it's literally like life is like a video, and it just stopped for like some of the stuff sounds like what people with really bad acid trips
right.
And So yeah, I mean, so the gist of that is that there is some benefit of SSRIs. I think there is a segment of the anti-SSRI crowd wants to claim that it's all smoke and mirrors, that they do anything good at all. I don't think that's true. I do think that it is true that the most powerful cure for depression in the literature is the placebo. And it's, it's so powerful that most clinical trials of depression do a placebo washout period where they put the people on the placebo for a week or more, and then everyone who has their depression cured is kicked out of the study. But then they still get 25 to 50% of people going into remission in the placebo group in these studies. So I've looked at, and there's hundreds of trials on nutrition.
Wait, are you saying that there's a lot of trials where they give people placebo? Many people improve, and they basically remove them from the rest of the study.
That's all the SSRI trials do that.
Wow.
Yeah. And that's because you're never going to show an effect of the medication if there's an 80% placebo remission rate.
Right.
But the idea behind that is BS. The idea behind that is that some people are more vulnerable to the placebo effect than others. And there is some truth to that, but I think if that was what drove the placebo response, then you wouldn't be getting average 25% drop in depression scores in the placebo group after you did the placebo washout, right? So you're getting a huge number of people that don't have their depression cured on the placebo during the placebo washout, but then they do get their depression cured on the placebo during the next 12 weeks, right? So the point is that, to me, when I see that, I'm like, oh, okay, well, that means that 50% of depression is mindset, and for a lot of people, the placebo provides enough hope and optimism that was the thing that pulled the switch in their brain. But then, you look at psychotherapy trials, and there are hundreds of trials. There are hundreds of trials on nutrients. There are hundreds of trials on exercise, and there are hundreds of trials on psychotherapy. Psychotherapy is generally outperforming placebo by 10 to 40%. What a placebo is in a psychotherapy trial is a whole other can of worms. But whatever they're calling a placebo, they're outperforming it by 10 to 40%. So that shows you that the average placebo effect is less than the total mindset relevance, right? So maybe mindset is 60 to 70% of the recipe, and biochemistry is 30% of it. But the average pill is, and you could debate whether psychotherapy is a more effective placebo than a pill is, or whether psychotherapy is more effective than the placebo, which is adequately represented by the pill. But at the end of the day, it doesn't matter. I think people get obsessed with the idea that the placebo effect's not real. The placebo effect is not the portion of the effect that was not real. The placebo effect is a portion of the effect that was due to mindset.
Right.
It's the whole point of psychotherapy is to improve mindset. So there really is no difference between it being a better, if psychotherapy is a superior placebo, that says that is a big deal for psychotherapy. That's a good claim.
Right. Yeah.
If they provide the optimal placebo, and the optimal placebo gets rid of 70% of depression, then the best badge of honor you could wear would be to provide the optimal placebo.
Yeah. So when someone goes on SSRIs, describe what's going to happen acutely in terms of serotonin in the body and in terms of the mitochondria in particular? How is the serotonin effect going to impact mitochondrial biology?
This depends what SSRI you're on, but let's talk about it generally, and then we can get into specifics. So at a general level, you are blocking serotonin uptake into a cell everywhere, and once the serotonin gets into the cell, you are blocking its uptake into the mitochondria. And then the SSRI itself is going into the cell and doing other things, which is itself is no one ever talks about that.
Right.
but so what, primarily outside the brain, what this is doing is it's causing you to pee out all your serotonin because
cells can't uptake the serotonin and you're peeing a lot of it out.
Right, because the way that you pee things out is basically everything goes out and then the kidney tries to take back what it wanted, right? And so if the kidney can't take back what it wanted, it goes into the urine. The other thing is the serotonin flux outside the brain is primarily made in the gut, gets stored in the platelets. So if it's not getting stored in the platelets, then it's going through the kidney into the urine. And if the kidney can't take it back up, you're peeing it out, right? So within 2 weeks, you've got a 14-fold decrease in circulating serotonin, which probably has a huge impact on the non-gut, non-brain serotonin. But because the brain is largely the producer of its own serotonin, or specifically the brain stem is the main producer of serotonin for the central nervous system, or part of the brain stem, and the gut is the major producer for the whole body, including the gut. Probably you are not depleting serotonin as much in the gut and the brain as you are in some of the cells of the rest of the tissues, where mainly they're taking serotonin up when the platelets are releasing it in response to hypoxic stress. But you could broadly say that the main effect outside the brain is just to get rid of your serotonin. But in the gut, you are also increasing the extracellular serotonin, which does not only act on neuronal synapses, it also acts on like all the other cells that have serotonin receptors, like smooth muscle cells have serotonin receptors. And this is, it's a very important point for the people that think that serotonin is a brain thing. It's like, well, there are neurons outside the brain. No, it's not a neuronal thing either. When serotonin is named for constricting blood vessels, it's not acting on the neurons that control the vasoconstriction. It's acting on the smooth muscle cells to directly contract them. So in the gut, you are overstimulating gut motility, hence nausea and vomiting as a side effect, and that tends to even off over time. Probably because probably because you're getting rid of the serotonin.
You're peeing it out,
right. So it's probably like maybe gut serotonin goes back to normal because production increases or something like that, but probably that increase in the extracellular serotonin ratio it's being taken care of by the whole body flushing into the urine.
But there's going to be just less serotonin uptake into cells overall. Therefore, serotonin is not going to do the stuff it normally does in the cells, which would include making melatonin to deal with things like hypoxic stress.
Right. At the cellular, at the subcellular level, the main effect is you're just obliterating intracellular serotonin and melatonin. Intracellular serotonin is not going to last unless it gets turned into melatonin in the mitochondria. So the main effect is you're obliterating mitochondrial melatonin. Now in the brain, you are kind of doing the same thing, but the brain's not in direct communication with the circulation of the urine, so you're not getting rid of it. You are just increasing the extracellular to intracellular ratio. And that does not mean that's not primarily a synaptic event. Yes, that is the target, but that also, there's plenty of parts in the brain where the serotonin receptor is responsible for getting serotonin that was made in the brainstem into the cell, so it can make melatonin inside the mitochondria of that neuron. And so the serotonin transporter is not only at the synapse; it's all over the place. And I think there's, you'll get conflicts in the literature about like, is serotonin, where is serotonin getting into the cell and where is it not in the brain? But I think a lot of that is a result of the context that you're measuring it in, because when you have stress responses, the cells will move the serotonin receptor to their membranes. So, you might have an experimental context where you're not getting a whole brain all over the place serotonin uptake, but you have an event of hypoxic stress in the brain, then all of a sudden all these neurons are expressing their serotonin receptor to get that to, take up the serotonin for themselves to protect their mitochondria. And they can't do that when the SSRI is blocking the uptake there because there's nothing that pharma doesn't have a way to get the SSRI to only go to the synapses that it wants it to,
right.
and not everywhere else. Now, the different SSRIs, all of the SSRIs will go into the cell. Some of them are 10 times more effective at getting into the cell than others. In general, the intracellular concentration of the SSRI is going to be the same as the extracellular concentration. Some SSRIs are like 10x more taken up by the cell, but it just winds up accumulating in the membranes. Maybe the membranes store it for later and maybe it gets released. No one really knows. But when they're in there, the SSRIs have a 52-fold different ability to stimulate the sigma-1 receptor, which is a receptor that lies at the junction between the endoplasmic reticulum and the mitochondrion. And it is meant to be activated intermittently during various types of stress, not just hypoxic stress, but also just psychological stress. So the glucocorticoid receptor will that whole response involves activating the sigma-1 receptor. And the sigma-1 receptor is a major driver of movement of the serotonin transporter to the cell membrane to take up serotonin and ramping up intracellular serotonin synthesis and ramping up the conversion of serotonin to melatonin in the mitochondria. So what happens is if you look at whole brain serotonin in animal studies, because they don't do these studies in people, SSRIs that are weak activators of the sigma-1 receptor cause a whole brain decrease in serotonin. And SSRIs that are good activators of the sigma-1 receptor cause a whole brain increase or just stays flat serotonin because the maybe like you have a equilibration of intracellular and you have a higher than normal amount of extracellular, but like the whole brain level it's kept preserved, or it's even increased by the fact that the sigma-1 receptor is what is increasing the synthesis of serotonin inside the cell. But that doesn't mean, a lot of these studies, they can't capture reality because the tools that you have involve like isolating different parts of the easiest thing to do is take the brain out of the animal and homogenize it. The difficult thing to do is to dissect the brain into different parts. Like you take out the hypothalamus, but you still have to homogenize it. And so you're getting to a whole level of like way more experimental difficulty if you're going to try to ask questions about different neurons within a brain segment and different mitochondria within that neuron. But it's even known that the response to serotonin or SSRIs is different mitochondria respond differently in the neuron. So there is a study where they took neurons from the cell body of the neuron, and they took neurons from the axon, and then they centrifuged the axonal neurons to get the heavier ones and separate them from the lighter ones. And no one really knows the difference between the heavy and light ones. Like people have done studies on what are some of the functional differences between heavy and light, but it's kind of, I would say it's more of a mystery than it is like a textbook kind of, this is what heavy ones do, this is what light ones do. But the point is that, you have three types of mitochondria from the same neuron. They're all responding differently to the SSRI in terms of mitochondrial function. So what I think to say that activating the sigma-1 receptor preserves the whole brain serotonin, that doesn't mean all that serotonin is all in the same organization as it was before. Yeah. I think what you have is you're increasing the, like in a non-stressed state, you have some neuronal synapses where serotonin is very active, and you have other neurons where it's not really that important. But in the stressed state, they're going to make their own serotonin. They're going to take it up. They're going to put it in the mitochondria and make melatonin. So if you're blocking the uptake of serotonin to the cell, but you're blasting the sigma 1 receptor, you can say like, oh, you preserved the brain serotonin, didn't go down, but yeah, it's probably in different places, right?
Right.
What are the implications of that? I don't know, but you're not, there's nothing natural. The thing, I say this mainly to combat the total mythology that was pulled out of pharma's butthole, which is that, depressed people have a messed up serotonergic system and SSRIs help normalize it. Like there's nothing, whatever the SSRI is doing, you're not restoring a natural state.
Right.
There's nothing natural whatsoever. I mean, even the sigma 1 receptor, like activating it is good, but it's not supposed to be activated 24/7 all the time.
Right. It's supposed to be intermittent.
What does that do? I don't know, but it's not natural.
Yeah. Interesting. That actually reminds me, there's I think there's some evidence out there that endogenous DMT activates that sigma 1 receptor and that it protects cells from dying in hypoxic conditions. And DMT is a tryptamine.
Yeah. Yes. That's right. DMT is supposed to be one of the endogenous activators of sigma 1 receptor. No one really knows like what is supposed to be the normal thing activating the sigma 1 receptor, but it's activated in hypoxic stress. It's activated in glucocorticoid stress. There are various like choline, sphingolipids, DHEA are all stimulators of it. Pregnenolone is an inhibitor of it, and DMT is an activator of it. But these studies with DMT, they show that it's doing, it has the same thing where under hypoxic stress, DMT helps preserve mitochondrial respiration. And I think it's through this same network of you activate sigma 1, take in the serotonin, make mitochondrial melatonin.
Yeah. So I guess one thing that's interesting here is if there's a way to preserve at least some mitochondrial function even under hypoxic conditions, even if you're only getting 50 or 70% of the ATP production, that's still a hell of a lot more than you're going to get if you were forced to use only glycolysis. So maybe the cell has come up with multiple ways to do that. Yeah,
I think that, right. I think that serotonin and melatonin, the primary thing that they're doing with relation to mitochondrial function is to allow more ATP to be made than could otherwise be made under conditions where oxygen is limiting.
Mm-hmm. One more prescription drug I want to briefly ask you about with respect to mitochondria are statins, right? So statins are the cholesterol-lowering drugs that many people take. It's known primarily for that role that it plays. What do the most commonly used prescribed statins do to mitochondria, if anything? I've seen some evidence out there that they mess with mitochondrial function, but what do we actually know?
Well, statins this is another example where people think that they conceive of the side effects as being off target when they're not. So the cholesterol pathway is it has many steps in it, and statins act on the production of mevalonate, which is a distant precursor to cholesterol. Mevalonate gets turned into many other things besides cholesterol. It gets converted into dolicol, which is a important substance for glycosylating proteins, which is the addition of sugars, which is important to their functions. And it's the precursor to the MK4 form of vitamin K2. That's not actually directly synthesized, but when you eat vitamin K1 from plants, you modify it to turn it into vitamin K2 in the MK4 form. And the MK4 form has a number of roles, but one of them is in the mitochondria. It acts somewhat similarly to CoQ10, but not in the exact same way. I think it's kind of an important release valve in the mitochondria, but regardless, it's important for mitochondrial function. And then CoQ10 itself, its tail is made in the mevalonate pathway. And then the precursor to vitamin D, 7-dehydrocholesterol, is also synthesized through this pathway. So you are inhibiting the production of all kinds of things. They include things that are important for mitochondrial function. And I need to look more into the mechanisms of this, but statins also indirectly hurt the synthesis of creatine, believe it or not.
Yeah. So the point is, the mechanism by which they lower cholesterol, it's not just they lower cholesterol, period. There's lots of other things being touched here.
Right. I mean, they're not acting directly on cholesterol. They're acting way upstream from it.
Right.
So you think you're on a cholesterol lowering drug, and the doctor can call it that, and pharma can call it that, because that's why, that to call it a cholesterol lowering drug is a marketing term. If you were to talk about it in biochemical terms, you would say that it's a mevalonate synthesis inhibitor. If you want to be honest about the biochemistry of it, you're inhibiting the synthesis of mevalonate. That's what you're doing. And that implies that you're inhibiting the synthesis of everything else that is a downstream product of mevalonate, which means that if someone gets myopathy from a deficit of creatine CoQ10, as an example, we know that myopathy is a side effect of statins. We don't quite know what the determinants of it are, but whatever they are, it's probably a result of inhibiting mevalonate synthesis. Effect of the statin, right? So it's an on-target effect of the statin. It did exactly what you designed it to do,
right?
It did exactly what you wanted it to do, but it didn't do exactly what you told the patient it would do in your marketing materials. So that means your marketing materials are off target. But I'm sure that some doctors resent this, but from the perspective of pharma, the doctor is like a MLM sales, door-to-door salesman type of unit, doctors get educated. The insurance agencies and pharma are so intertwined in the medical literature and medical education that effectively the way the system works is that pharma is using the doctor as a salesperson for the statin. So what the doctor is telling the patient is effectively marketing materials for pharma. And so they're not quite honest about what it's actually doing on a biochemical level. But the randomized controlled trials do not support CoQ10 co-supplementation to mitigate even the myopathy that comes from statins. So I do think it's more complicated than that. My suspicion is that CoQ10 is part of the puzzle, but it's not 100% of the puzzle, and it might not be sufficient by itself to solve the average case of myopathy.
So, there's so many things that we could talk about here, all sorts of different drugs, and we can talk about nutrition all day long, but mitochondrial metabolism is super important. This is how our cells make most of their energy. And in many ways, the modern environment is hurting people's mitochondria in different ways. We've touched on some of those. What have you been working on to help improve mitochondrial health in people, and how did you get down this path?
Yeah, well, just to tie it back to what we were just talking about super quick, one of the ironies of taking a mitochondrial poison like a statin to reduce your cholesterol as a first resort before optimizing your mitochondrial function is that we know how cholesterol gets taken up from the blood into the cell. It's to stimulate the production of the LDL receptor. And statins take cholesterol up into the cell by creating a deficiency of cholesterol in the liver cell so that the liver makes more of the LDL receptor, sends it to the membrane, takes the cholesterol in. But what people never pay attention to is how mechanically does the LDL receptor bring the cholesterol into the cell? Mechanically, it brings it in on a motor that is called dynamin, that's powered by mitochondrial ATP production. So the kinetic energy to bring the
LDL particle containing cholesterol into the liver cell is powered by mitochondrial ATP production. And so, yeah, statins do work to lower cholesterol, but if you have a deficit of mitochondrial ATP production, you should want to fix that before you take a mitochondrial poison, because then you can kill two birds with one stone instead of lowering the cholesterol at the expense of everything else that you need mitochondrial ATP production for. So anyway, to answer your question, I have founded MitoMe, which is a mitochondrial testing company where we take a cheek swab that then allows us to isolate mitochondria and measure each complex of the mitochondrial respiratory chain, which is where 90% of cellular energy in the form of ATP is produced. And I've seen other mitochondrial tests out there where, they'll tell you that you have a bad mitochondria, or they'll tell you that you have oxidative stress or whatever, but the results don't have any clear actionable insights. And the reason that we test the things that we do is because we can look at the different parts of the machinery that you use to produce ATP that have different implications for nutrition and other non-pharmacological interventions. And we can actually make actionable insights to say, well, Nick's mitochondria look a little different than Chris's, and the limiting factors for Nick's mitochondria are different than Chris's, so Nick should be doing something different than Chris, right? So there are things that you can say that everyone should be doing for mitochondrial health, like everyone should be getting enough sunlight, everyone should be eating a nutritious diet, everyone should be getting enough of the right type of exercise, et cetera, et cetera. And there are supplements that will probably benefit everyone. Like the average person would probably do well to try creatine supplementation, for example. But there's a lot of stuff where we each have idiosyncratic needs. And I was motivated to go down the idiosyncratic genetic nutritional need rabbit hole a couple of years ago, due to my longstanding speculation about myself that my entry into the nutrition space 20 years ago was driven by a really bad experience on a vegan diet that really just completely turned around on a diet that was Weston A. Price style with organ meats in it. And so I spent a decade or two thinking, I know that I don't think veganism is the most robustly beneficial diet that anyone should be on. Like probably everyone should have at least some animal products in their diet. But there was something strangely catastrophic, and not only strangely catastrophic about the vegan diet for me, but just bizarrely miraculous about a diet rich in organ meats that made me think that there's something unique about my nutritional needs. Like I'm unable to synthesize something important.
Do you mind telling us what was so catastrophic? Did you just have low energy?
Okay. I would say there were kind of three axes of it. So my teeth fell apart. I had 15 cavities and needed 2 root canals after I was vegetarian for 2 years, vegan for a year in the middle. And my gut was definitely not working well, but you could attribute that to eating a lot of things that are difficult to digest. But the big game-changing thing for me was my mental health. So I did have anxiety problems as a teenager that were probably largely connected to marijuana use when I was in my early teens. But it just went to like borderline psychotic levels of phobias and OCD, et cetera. And like to the point that like I was not able to eat, and I had lost, like I looked like I was anorexic. And I found out about Weston Price's work. Mm-hmm. Weston Price was a pioneer in nutritional anthropology. The gist of what he promoted was a diet rich in fat-soluble vitamins from animal products, especially shellfish, organ meats, eggs, dairy products. And he had plenty to say about healthy plant products as well, but that was kind of the the big take home that contrasted with my vegan diet.
Mm-hmm.
And so I wanted to fix my teeth. He did say a little bit about mental health, but not that much. He was a dental researcher turned nutritional anthropologist. So it was mostly about teeth. And I had this mouthful of cavities. So it was like, well, immunity to tooth decay. I want in on that. And so I changed my diet around. I'm not even thinking that my mental health would benefit from it all. But the point at which I realized that it had was I was an undergrad working in the dining hall, and I saw a guy pick up a pile of plates and take one from the middle. And I had just put the plates out. So I'm pushing the cart of plates back into the middle room. And I just, in my own head, I mocked the guy a little bit. I'm like, that guy's kind of a weirdo, why didn't he just take the plate from the top? It's a little bit neurotic. And then I just had this light bulb went off in my head. And I suddenly remembered that 3 months ago, I would spend 20 minutes picking out a glass that was clean enough to drink out of, that didn't have any spots on it. That was like the least neurotic thing that I'd done with my food. But it was like the thing that I was mocking that guy for was, 20 times less severe than the least neurotic thing that I had been doing a few months earlier. And that was shocking to me because I had totally forgotten that I was like that. So it really came up as a surprise, but I was like, wow, like I had totally forgot that I was completely neurotic, just a few months ago. And so it just sort of hit me that like, wow, this like completely revolutionized my mental health.
Why were you doing the vegetarian vegan diet to begin with? What was motivating that?
Oh, well, I read the book Diet for a New America by John Robbins of Baskin Robbins Inheritance. And he told me that it would be good for the planet, it would be good for the animals, and it would be good for my health.
Okay, so then you had that experience. And then you at some point you start.
I have since decided that he was wrong, but
okay. So tell me, how does this Mitome product actually work? It is a cheek swab. I've done it. We can talk about my results a little bit to show people. It's really interesting. But what are you actually measuring here when you're measuring, the activity levels of each complex of the mitochondrial electron transport chain? What is the assay that you do?
Well, there's basically 5 assays. You might say 6, because everything is normalized to the amount of protein extracted. But citrate synthase is measured, which is a citric acid cycle enzyme. The citrate synthase is it can get up and down in its expression, but it is generally considered a decent, although not perfect, marker of mitochondrial density. And so all of the respiratory chain complexes get normalized to the citrate synthase, which in turn gets normalized to the protein content. So it's basically, okay, we know how much stuff we extracted, and then out of that stuff, how much of that represents mitochondria, and then out of that, what are the activities of the respiratory chain enzymes, and the respiratory chain enzymes. So the mitochondrial respiratory chain is where 90% of ATP is made. ATP is the general energy currency of the cell. And you can think of that as happening in 2 stages. First is you have macronutrients like protein, fat, and carbohydrates. And one stage is, can you go to the, let's go to the, yeah, that one. You just passed. Yeah. Okay. Yeah. So,
sorry.
Yeah, there we go. So yeah, you eat protein and you digest it to amino acids. You eat fats, you digest it to fatty acids. You eat carbohydrates and you digest it. In glycolysis, you break it down to pyruvate. And some of those fats can get broken into ketone bodies, and all of these things can produce acetyl-CoA. This is somewhat simplified. They can also produce various intermediates in the citric acid cycle. But you can broadly think of this as metabolism happening in 2 stages. The first stage is you want to break down the carbon bonds within the macronutrient molecules. So within the amino acids, fatty acids, or carbohydrates. And then you want to harvest the electrons while they are in high energy states that are associated with those bonds. And then the second stage is you want to carry them down to the respiratory chain. So you have molecules like NADH and FADH2 that carry them down to the respiratory chain. Why don't you go, down to the one before that. Well, either one of these is good. So, we'll settle on this one. So, you are in the respiratory chain. Actually, go up to can you go up to the first picture and just zoom in on the respiratory chain? I think that's better.
Oh, yeah.
Yeah. Okay. Just can you enlarge it and zoom in there? Yeah. Okay. So you have these complexes, and this is showing them in reverse order: 1, 2, 3, 4. ATP synthase is often called complex 5, but oftentimes it's just called ATP synthase.
So these are all proteins in the membrane of the mitochondria within our cells.
Yep. Okay, so if you were to release all the energy at once, you would basically just blow up. And that would be like, a good analogy is a car. If you want the car to go from place A to place B, you don't light a match and throw it in the gas tank. Lighting a match and throwing it in the gas tank does combust the gas in the same way that driving from point A to point B is, but it combusts it all at once, which is, not conducive to turning the tires at a speed that are going to get you to a place in the time you're trying to get there. It's too much energy at once. It just blows the car up.
Yeah.
So, what happens is you have mechanisms within your car to allow you to combust small amounts of gas at once, harness it way more efficiently than you would, right? Like if you blow up the gas tank, you've released the energy. It's just you didn't harness any of it. Like all of it went into the environment and blew the car into the environment. If you harness little bits at a time, you're able to harness it efficiently so you can do something with it. Mm-hmm. So in the respiratory chain, you actually have many dozens of sites of electron transfer, and these are grossly simplified in this diagram into these 4 complexes. Within those complexes, you have multiple sites of iron, sulfur, vitamins, etc., that are allowing you to take these high energy electrons from the food and feed them through one step at a time. I don't want to go through. I don't want to go through the whole report. So we can.
Okay. So you're basically able to measure.
Stop the screen share here, and we can just talk about it.
Yeah.
So what you're trying to do in the respiratory chain is pass each electron through dozens of times, where each time you can harness a little drop of energy from it, and so that instead of harnessing 1 or 2% of it, you're now able to harness like 50% of it, and you can use that to synthesize ATP. But you're still evolving like half of it is heat, and then there are ways to turn that that amount up or down. But in the respiratory chain, there are 297 gene products where you have complexes that are just complex 1 has a few dozen proteins that compose it. But the ability to measure each of the complexes allows us to say, like, okay, there might be 297 genetic idiosyncrasies that could be producing your primary bottleneck to produce cellular energy, but there are broad generalizations that we could make across those, where we, instead of doing a genetic analysis where we're pinpointing highly specific genes in one of those complexes and speculating that gene might be powerful enough to have an impact on that complex, we can just measure the complex directly. We know what is happening in that complex because we're doing the biochemical assay, and that allows us to make inferences about the needs of that complex on a nutritional level, or based on patterns, where we can say, oh, that's high, that's low, that's in the middle. That is a pattern that you would see if such and such a problem were your limiting bottleneck. And so that allows us to make inferences about things like, would you need more of some of the cofactors involved, like iron, copper, sulfur, riboflavin, niacin, and so on? Or, in some cases, do you need to modify the amount of exercise that you're doing? Or do you need to modify the, or do you have a potential relationship to the hypoxia response? So, for example, we were talking about with SSRIs, that serotonin is fundamentally modifying the hypoxia response. There's also patterns that you see in the respiratory chain that could be indicative of chronic exposure to too much hypoxia, or even, not enough hypoxia. And these things can become very relevant to depression because, one interesting animal study showed that intermittent hypobaric hypoxia training had an antidepressant effect that lasted 25 times longer than produced by an antidepressant drug. So the Mitochondrial test will allow us to see things like, do you have too much hypoxia response, or do you have the signature not enough? And how could you modify your diet, supplements, and training regimen in order to better calibrate your regimen to the needs of your mitochondria?
So let's make this a little more concrete for people. So you've got all these mitochondrial complexes. You guys can measure how much they're working. So my results were that I had high normal activity in complex 1 and for citrate synthase. Everything else was labeled as normal. So how do you start to interpret that? And what does that start to tell you in terms of things like the macronutrient composition of my diet? So why would someone like me have maybe a high normal amount, high normal for complex 1 and citrate synthase?
So the citrate synthase marker is a marker of mitochondrial density, and at a level where it's just high normal, the main impact is that you're going to be interpreting the rest of the complex as normalized to it. So if citrate synthase is, you don't want, like, if you look at presumably healthy people over time, what you see is their mitochondrial density generally goes down
right
across the aging cycle. So you generally want to be in the high normal area relative to your age while you're aging, because that probably means that you're keeping up with,
you're not losing your mitochondria.
Healthy level of mitochondria. But you can also see, like, certain poisons, or for example, might 5x the mitochondrial density because you have, because you're unable to make ATP, and so your mitochondria are reacting to an adverse stimuli. Generally that's going to be a good thing. And then higher complex 1 than 2, as an example, could have macronutrient implications for your diet, because
So like I was recommended a high carb diet as opposed to a high fat diet. How do those things fit together?
Well, if you look at how carbohydrates and how fats flow into the respiratory chain, you see that carbohydrates are more using complex 1 than 2, and fats are more using 2 than 1. So in that case, the results are consistent with a requirement to have, for the bias of the diet to be towards carbohydrate rather than fat. And generally in the protocols, we walk people through multiple examples of multiple steps that might improve the balance, and then things that might work around an imbalance. And someone who, for example, had a deficiency of another complex, their protocol would look different than yours, because the macronutrient suggestions are going to be put in following attempts to fix things that are low. Because part of the logic of the protocol also is we're walking people through the process of how to empirically test whether things are working for them, because there are suggestions that come out of the data, but then ultimately empirically you have to test what works best for you. So someone could have a deficit in a complex where they might have a suggestion of a high fat diet or a high carbohydrate diet, but we would go through first, if this is fixable, here's how you would fix it. So try to fix it first. And then at that point, that would be the time to see whether modifying your macronutrients makes sense. And then we also have suggestions for people if they're struggling with a step on a macronutrient related suggestion where what are some of the things that might be hurting your ability to work in that step, and then we'll help people figure those things out and go through it to test the impact on themselves.
And what would be your suggestion around like the type of person that would most benefit from this type of test? Like how would one know that they should consider looking at something like this?
Yeah, I could frame this in a couple different ways. So let's say that we could consider three types of people. So we could consider the people who are they don't have a lot of time to invest, but they don't care about whether they have to spend some money on something. It doesn't mean anything to them. Then we have people who they really want to, they have a lot of time and they don't have a lot of money. And so they're much more ready to invest their time. And then we have people who are kind of middle of the road and are just trying to do things in the optimal way. I'll start with the middle of the road people. So, if you have a budget for health testing and you want to be strategic around how you use it, then I would say that you want to, well, first of all, everyone will benefit from knowing how their mitochondrial function and whether there's a limiting block in their mitochondria, because your ability to produce cellular energy is determining your ability to leverage all your strengths and to fix all your weaknesses with respect to your health, wellness, and longevity. So everyone would benefit from knowing whether there's a fixable bottleneck in their mitochondria. If you are trying to play the middle of the road and use everything in your budget strategically, what you want to do is you first want to make sure you're hitting all the low-hanging fruit of good health. And you then want to analyze your nutritional status and make sure that you don't have any missing nutrients. And the reason is you don't want to be missing out on something that you could have easily fixed yourself, and then just be told to do that thing with a test that you spent money on if you're trying to use your resources strategically. Now, comprehensive nutritional testing is actually a lot more expensive than the Mitome test. So I would actually recommend that if people are trying to save money, that it's better to test the Mitome than to do comprehensive nutritional screening, because our protocols do actually walk people through what nutritional tests would be beneficial to them if they were trying to implement the protocol with more testing. But there's a lot of things that you can do at home to check whether you're getting your nutrients. So for example, you can track a representative sample of your diet in Chronometer. And as long as you follow best practices for tracking, you can have a really solid dietary analysis that can tell you if you're running short on any nutrients. And, and I have on my website, on my Substack, if you click on nutrients or you click on, actually, I would say people should visit my post, what everyone should be doing for their health. There's a checklist there. That's a good starting place to make sure you're checking all those boxes. And then you can just follow the post through, just go to the bottom and click on the next one. It'll guide you through some testing ideas. But as you click into the next few posts, you're going to come across how to track your diet in Chronometer. And I give best practices and I give custom nutrient targets, right? So follow the best practices, put the custom nutrient targets into Chronometer. And if you see that you are getting 50% of what I recommend for thiamine in your diet, now is not the time to dump money into testing just to tell you to take thiamine. Now is the time to say, okay, what can I eat differently, or what should I supplement with to fix that? And you want to be, and this is another thing. A lot of people think that when you do nutritional testing, you want to cut out all your supplements to get some sort of baseline. Or when they're doing the Mitochondrial testing, they ask the same things like, should I get rid of all these things so I can test the pure mitochondria? There's no such thing as a pure test. There's no such thing as a pure baseline. Like, you weren't even born into a pure baseline, because you were born 9 months into all the things that your mother was doing while you're pregnant that are impacting the nutritional status and epigenetics that you were born with. And now you have 20, 30, 40, 50 years behind you with all kinds of things that you've been doing that, like, right? So what you want to do is you want to be doing the best practice, where you are doing everything you can for yourself that, as far as you know, is what is the best of what you can do. And then you want to say, okay, now me getting to the next level is limited by the information I could get. Now's the time to test. But that's the optimal strategy to use it. But for people that, money is not a limiting resource for them, what I would do is I would just test Mitochondrial as well as comprehensive nutritional screening, as well as everything else under the sun, every time you want to change your protocol. So you just have a comprehensive data set of, like, I started eating liver, and then, my testosterone doubled, but my cholesterol went up too high, and the Mitochondrial results showed my complex 2 went down. And, like, what can I synthesize out of that? And then I think if someone is, it just has no money and has all the time in the world, then what you really want to be doing is and I'm going to be producing more resources for, like, the budget conscious self-experimenter. But what you really want to be doing is you want to be exhausting kind of, what can I learn? What can I try? And how do these produce results for me? And if you have health insurance, then maybe you can do testing that's covered by health insurance at Quest and LabCorp to assist you in that. But, if you're paying out of pocket for all the testing, then what you really want to be focused on is things that are actually measurable at home. And so you can measure your body weight, you can measure your waist circumference, you can measure, you can self-rate the things you care about on a scale of 1 to 5. How's your energy? You can, women can look at whether, how regular is their cycle, how well is it conforming to a lunar cycle versus, irregular, too long, etc. All these things that you can track for yourself at home. And then when do you do the testing? You do the testing when you run into a wall and you say, there's something I am unable to fix. I've run all the experiments I can think of. I now know for a fact that I'm limited by the next piece of information. And then, then that, just goes back to, you're now, like, in the strategic use of the testing, you're now at the point where you would run the Mitochondrial test, because your diet's as dialed in as you can get it. Mitochondrial test is going to tell you not only how your mitochondria is functioning, but it's also going to tell you what nutrients could be limiting. And, if you want to test other tests of nutritional status, these are the ones that you would test, and this is how you would use them.
Are there any final thoughts or anything you want to leave people with or reiterate from our discussion, especially as it relates to mitochondrial health?
Yeah, I would leave you with this. So your mitochondria are what are producing your cellular energy, and your cellular energy is what governs your ability to fix your weaknesses and your ability to use your strengths. And it's going to govern everything from the ability to get out of bed in the morning for someone with chronic fatigue, and the ability to convert a silver medal to a gold medal in the Olympics, and everything in between. And I have an article from a few years ago called Energy Metabolism Governs Everything. If any of this sounds counterintuitive to you, then I would highly suggest going to my site and reading that article, because that's a succinct argument for why your ability to produce cellular energy in the mitochondrial respiratory chain in the form of ATP is literally governing everything that happens in your body. And this is built into the laws of physics. A lot of people cite the first law of thermodynamics, which is about energy conservation, when they're telling people why they have to have a caloric deficit to lose weight, or why they need a caloric surplus to gain muscle. Not many people cite the second law of thermodynamics, but the second law of thermodynamics says is that everything falls into chaos if you don't input energy into the system to prevent that. And so if you look at aging, like, why do we fall apart as we age? It's because we're not efficiently extracting energy to invest in preventing entropy from accumulating according to the laws of physics. Or if you just, and what does that mean? What is chaos, or more scientifically entropy? If you look at health, be polarizing into a highly organized state is the opposite of that. So, for example, if I want to extremely well contract my bicep when I'm doing an arm curl, but I want my arm to be relaxed when I'm not doing an arm curl, then that is a high energy state. People think they only invested energy in the arm curl, but they're actually investing energy in relaxing their arm as well. The low energy state is to not be able to tell the difference. It's to have your bicep cramping when you're not trying to do an arm curl. It's to have your bicep twitching when you had done an arm curl 3 hours ago. Those states of not being able to compartmentalize heavy contraction and relaxation is a low energy state. Being wired and tired is a low energy state. The high energy version of that is having really deep sleep, really powerful REM sleep with peaceful but creative dreams, feeling super rested when you get up, and then being high energy to attack the day, not getting sleepy in the middle of the day, not feeling like you're falling asleep at your desk because you can't motivate yourself to work, feeling like you have all the energy in the world when you're trying to be awake and alert, and that you have total relaxation at night to get all the sleep that you need. These are high energy states. So across the board, from moving from disease to health, moving from just not being diseased to actually being functionally healthy and optimizing your wellness, and into maximizing your performance at work or in sports, and to living a long, healthy life, not just a healthy life right now. All of those things are about maximizing your cellular energy production. And half the things that we need to do that are going to be things that we all need to do, like eating a nutritious diet, getting the right amount of sunlight, getting the right amount of exercise. But the other half of that is figuring out what our limiting bottlenecks are, and feeding our unique needs with those inputs. And there are different ways to do that. Some of them are more around self-experimentation, and some of them are around testing. And what Mitome is really trying to do is bridge that gap and do the optimal testing at the source of cellular energy production, but then also give you the things that we think have a high probability of working, but also guide you through the process of how to turn that into your own self-experiment to empirically test it. And I think this is something where I think I, as a scientist, am helping people understand that really, even in medicine, if a doctor is prescribing something, they're using a model to predict that will work well for you. And ultimately, you do have to test whatever that is yourself. And so I do try to bring this scientific consciousness into all the protocols that I make, so people can wrestle with the reality that listening to their body is the ultimate endpoint that they need, and all the testing is meant to facilitate that and to help you in the course of that. But ultimately, what you're trying to do is you're not trying to optimize the test, You're trying to use the information from the test to optimize your body, and you are the ultimate judge of whether that is working.
All right. I think that's a great place to end it. Chris, thank you very much for your time. And check out Chris's Substack. I highly recommend it. Hope to talk to you again at some point in the future.
Awesome. Thanks, Nick. This was great.
Visit mindandmatter.substack.com to find all of my content. Hey everyone, I want to take just a minute to tell you about one of my cool new affiliate partners called Seed Oil Scout. Seed Oil Scout has a really cool map feature that helps you find restaurants in your area where you can find seed oil free options. They also have a really cool product scanner, so you can take out the app and use the camera functionality of your phone to scan products in grocery stores and see what's actually in these things. Do they contain seed oils? Do they contain other things that you want to know about that aren't necessarily on the box? This will help you find places to eat and find foods to eat that actually have what you want in them and help you avoid those that don't. So if you're looking to cut back on your seed oil consumption, or you just want to know more about what's in the foods on the shelves at the grocery stores, download Seed Oil Scout today. If you go through the link in the episode description, click into that and you'll see a link to the Seed Oil Scout app. If you go through that link on my support page, you'll be directly helping the podcast, and you'll be able to download this really cool, easy to use app that will help you find healthier food options. So go through the link in the episode description and download Seed Oil Scout today.